We're now going to look at the graphs of trig functions, and I got a unit circle here. So as this thing spins around here, for any given theta, it connects, or it corresponds to a point on the unit circle, and the sine is the y-coordinate on the unit circle, the cosine is the x-coordinate on the unit circle, and the tangent is y over x. So let's see how we would graph these, given that that this axis, in this case, this is going to be theta, and over here, this is our y equals sine theta. And let me just, I don't want to confuse this y with the y on the unit circle, even though in this case they're the same. So this will be my theta, this will be my sine theta. Okay, now there's these four important points on the circle. Those are known as the quadrant angles. So 0, pi over 2, pi, and 3 pi over 2. Okay, those are known as the quadrant angles, and they correspond to the points 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, so the y value, okay, that's kind of the vertical distance that you are on this unit circle. The y value is going to start out at 0. It's going to go to 1, and it isn't going to go any larger than 1. It's going to then go back down to 0, and then back to negative 1, and then back to 0 again, and then it's going to start over. So each time around the circle, it repeats itself. Okay? And so when you graph these, what you're going to do is you're going to put the quadrant angles here. Okay? And here's the way I do it. So I'm going to put a whole period here. So the period here is 2 pi. And a period is every time the graph repeats itself. Okay, so to get the quadrant angles, I'm going to split that in half, and that'll be pi. And then I'll split this in half again. That'll be my pi over 2. And so this one is my 3 pi over 2. Okay, and similarly over here, this will be negative 2 pi. And then I'll split that in half, and I'll get my negative pi. Splitting this in half gives me my negative pi over 2. And then splitting that in half gives me my negative 3 pi over 2. Okay? And so these are the quadrant angles. And now the graph of sine is going to oscillate between negative 1 and 1. So I'll put 1 here, negative 1 down here. Okay? And this is going to be it's going to form a wave that oscillates up and down. And I can do those dashed lines there to represent the top of the wave and the bottom of the wave. And the sine starts at 0, and by the time you get to the end of the first quadrant, 90 degrees, it's up at 1, right? And then it goes back down to 0 at pi. The y-coordinate is 0. And then at 3 pi over 2, it goes down to negative 1. And then when you get back to 2 pi, it goes back to 0. Okay? And if you go this direction, the negative direction here, okay, it's, in fact, this is going like this. This is just going to continue the wave. So this will be down at negative 1. This will be up at 0. This will be up at positive 1, and then 0. Okay, and then the way to draw this wave is it'll be kind of curved like that, and then like this, and then like that. And this is one cycle of pi, okay? And then if you keep going, it would go through a second cycle, and a third cycle, and a fourth cycle. It keeps repeating itself. And then this goes down here, up here, and then like that. And so that's 2 cycles of pi, okay? So the domain here is just negative infinity to infinity. Doesn't you can put in any number. This thing can keep spinning around positively or negatively either direction, and so any real number can be put in there. The range, however, is just between -1 and 1, and it does include the -1 and 1, so we put square brackets. And then another important thing is the period. Okay, the period is 2 pi, and that's the amount of time or whatever it takes to complete a cycle. Okay, and then finally you have this amplitude, and the amplitude is just the distance from the center out to the peak, either way. Okay, from the center to the maximum or minimum value. So the amplitude is just 1. Okay, and so the amplitude, or the distance between the minimum and maximum values, is 2 times the amplitude. Okay, and that would be the graph of sine. It's a wave, a sine wave, right? So what about cosine? So cosine is very similar. This is like theta, cosine theta, except now it's the x-coordinate on the unit circle. And the x-coordinate is like this horizontal difference, and it starts out at 1, and then it goes up to 0, and then down to -1, back to 0, and then up to 1 again. So I'm going to put the quadrant angles on here again. So that would be 2 pi. This would be pi. This would be pi over 2. 3 pi over 2. And this would be -2 pi. Half of that is -pi. This is -pi over 2. And then -3 pi over 2. And then you have 1, -1. And the difference here, this is very similar to the sine wave, except here at 0 it starts at 1, and then it goes down like this to 0, and then it goes down to -1, up to 0, back up to 1. So it would look like this. Okay, so that's actually what the first cycle of cosine looks like. And then similarly, this goes to 0, down to -1, up to 0, up to 1 again. And that would be your cosine wave. Okay? And it's really the same wave as this, it's just shifted over. So if I took this wave and just shifted it back 1 quadrant, it would look just like the cosine wave. Okay? So they're pretty much the same wave, they're just starting in a different place. Okay? And similar, all these are the same over here. Okay? The domain is -infinity to infinity. The range is -1 to 1. The period is 2 pi. The amplitude is 1. Okay? So what about tangent? Okay? Now tangent is very, very different. Okay? So the tangent is the y over the x. And one thing I told you earlier is, as this spins around, the tangent is the slope of the line that's spinning around. Okay, the slope of the radius of this circle as it spins around. So like the slope here is 0. When you get up to 45 degrees, it's 1. Okay, so pi over 4 would be 1. And then when you get up here, it's undefined. It's a vertical slope. And then it's negative down to 0, and then positive again, and then negative again. Okay? So, let's put these quadrant angles on here again. You get real used to putting these in there. Okay, so the tangent is the y over x. So one thing to realize is whenever the x-coordinate is 0, this is going to be undefined, right? Because the tangent of theta is y over x, or you could think of it as sine theta over cosine theta, is another way to think about it. So whenever the cosine theta is equal to 0, you're going to get a 0 in the denominator. This is going to be undefined, right? So you have these asymptotes through those. Okay, so there's going to be an asymptote at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Okay, those are a little bit off there. But what the tangent does, so it kind of starts out at 0, a slope of 0, and then as you go around, it goes up to infinity. And this thing actually looks like this. It would go up like this, it would go down. Because when you go this way, it's negative infinity. Okay? And this is actually a full cycle of tangent. Because what it's going to do is it's just going to keep repeating itself. It's going to keep doing that. Okay? This would go up to this. And if you went on, it would just go up like that. This will go up like that. And this would kind of go up like this, right? And then if this went on, this would repeat itself. And you just get the same graph, but you get it every pi units. So the period in this case is not 2 pi. The period is only pi. Okay? And the domain is a little tricky too, because the domain here is going to be all real numbers except for pi over 2, 3 pi over 2, so on. Okay? And so the way you write the domain here, what I should say is I should start by saying all real numbers except x equals pi over 2, so that, except for that one. I can't list them out because there's an infinite number, but what I can do is I can say plus k times pi. And this is where k is an element of the integers. So z here stands for the integers, and the integers are just the positive, negative whole numbers. So this would be when k is 0, you get pi over 2, and then you would add another pi, you would get this one, another pi, you would get that one, so on. Subtract pi's, you would get the other ones. So that would be the domain. The range here, in this case, it's all real numbers, negative infinity to infinity. No problem. And it does it over and over again. Okay, the period in this case is just pi. It's going to repeat itself every pi. And then the amplitude here, well, the amplitude is the kind of the height of the wave. In this case, you don't have a maximum and a minimum height. So really, the amplitude in this case would not apply, right? And so there you go. That's sine, cosine, tangent. And what I did here is I printed this off to give you all 6 graphs here. And this is sine and cosine. And notice also, normally we're going to write this as y equals sine of x, not sine of theta. Okay? So what I was doing here is I was letting theta be the angle, and then the y would just be, for sine, it would be the y coordinate on the unit circle. For cosine, it would be the x coordinate on the unit circle. For tangent, the y would be the x over y, or the y over x, right? So normally, you don't use theta, you just use x, and then y is the value of the trig function. But this x here is not the x on the unit circle. The x is the angle as you go around. And then the y value is whatever the value of the trig function is. And that's the normal way you do it. So this is the sine, and we've already looked at that. It starts at 0 and goes up, and it just keeps doing the wave. Cosine starts at 1 and goes down. It keeps doing the wave. Okay? So these are the graphs of, this is the cosecant and this is the secant. So the cosecant is a lot like, or it has a relationship with the sine. and the secant has a relationship with the cosine. And it's very easy to see here, and it's pretty easy to graph, because whenever the sine is 0, right, then the cosecant's going to be undefined. That's where the asymptotes are going to be, okay, because you'll get a 0 in the denominator. So wherever this crosses the x-axis, you get this 0 in the denominator, and you get the vertical asymptote. And basically what these do here, they look like parabolas, but they're not. They approach the asymptotes here, but they approach it, they go down, and they touch right at those crests, and then they go back. Okay, so like this one would go, it would go down, touch here, go up. This would go up, touch here, like that. This would go up, touch, like this. Okay, and so this is what it would look like, except you wouldn't have this part. This is the graph of the sine. Okay, you would only have these pieces, and that would be the cosecant. And so the domain here would be all real numbers except, and here the problem is every pi, right? 0, pi, 2 pi. So it'd be except x equals just k times pi. That's all you have to do. When k is 0, you're here. When k is 1, you're here. When k is 2, you're there. When it's -1, you're here. So that would be the domain. The range here, well, this thing is going to go down. It'll take on 1, and then it'll go back up. Okay, and then -infinity up to -1 and back down. So you would actually do -infinity to -1. It would include the -1. And then you would go +1 to infinity. Okay, and then the space between, it wouldn't be in the range. Okay, and the period is 2 pi, just like the sine. And then the amplitude, well, it doesn't have a minimum or maximum value, so I would say the amplitude does not apply. Okay, and very similar here then. So where these cross the axis is where you're going to have the asymptotes, right? And then this will go down, touch, come back up, go up, touch, go back down, kind of like that. And that's what you're getting here. Okay? And again, the domain here, this is going to be all real numbers except, and this will be like the tangent, x equals pi over 2 plus k times pi. It'll be like the tangent because this will have a vertical asymptote whenever cosine is 0, just like the tangent, whenever the x-coordinate on the unit circle is 0. Okay, the range is the same as this, so it'll go from -infinity to -1, and then 1 to +infinity. And again, the period is 2 pi, and the amplitude does not apply. Okay, so this is the tangent. Remember, it had these vertical asymptotes, right? And it went from -infinity up to +infinity. It did it every pi. Okay? The cotangent is going to have the vertical asymptotes the same place that that the sine does, because the cotangent is actually equal to the x over y. So whenever sine is 0, that's when you're going to have, it's going to be undefined. You're going to have the vertical asymptotes. So that the sine is 0 at pi, right? It's 0 here at the y-axis, at pi, at 2 pi, so on. negative pi, negative 2 pi. And this graph is actually the same as the tangent graph, except it's flipped. It's what's the word? Reflected kind of there through the middle. It's just flipped over. Okay, so it's kind of like if you take the tangent, flip it over, and scoot it down pi over 2 units, you would get the cotangent. Okay, they're related in that way. And then for this one, the cotangent, the domain would be all real numbers except x equals k times pi, so a lot like the cosecant. The range is going to be negative infinity to infinity. The period is like tangent, and that's equal to pi, and amplitude does not apply. Okay, so there you go. Those are all 6 trig functions. Hopefully that helps you make sense of those. So now what I want to do, and I'm going to mainly concentrate here on sine and cosine, because these waves are kind of fun, and they model a lot of interesting behavior. Anything that kind of oscillates and has that periodic behavior, the sine cosine could be used oftentimes to model the behavior. So the amplitude and vertical shift, basically, let me just show you an amplitude change. Okay, so if I had something like 3 sine x, that 3 here is going to change the amplitude. Okay, so this is like 1, 2, 3, 1, 2, 3, right? Negative 3 to 3. And this will be like 2 pi. And this will be like pi. And then I'll just mark those. I won't label them. So this is negative 2 pi. Negative pi. And then I'll mark those. And the sine just kind of goes up to 1, right? Like this, down, down, and then up like that. And I'm just doing this dotted because I'm not graphing the sine. I'm graphing 3 sine x. Okay? So the 3 sine x, it'll be the same as this, but now it's going to go up to 3, back down to 0, and then down to 3, like that. And so this is like a period change then. And I didn't do the best job there, but the idea is this stretches the wave out. It kind of makes the wave bigger, okay? So you could also have a negative number in front, and that's going to also flip the wave. So if I have like y equals, let's say, negative 2 cosine x, let's say. Well, that'll flip the wave here, so we'll say 1, 2, 1, 2. And we'll say this is negative 2 pi. We'll say this is 2 pi. We'll say this is pi, negative pi. And then put the halfway marks there. And the cosine normally starts at 1 and goes down like this, right? And so that would be your cosine. And so this is going to stretch it out too, but it's also like when this was, when this is here 1, a negative would bring it down and make that value the opposite, right? So this thing is going to start at negative 2 and go up like this. And this will go yeah. It'll look like that, okay? And one nice thing about this cosine here, is that it starts at a minimum value and keeps raising, right? Because normally it starts at a maximum value, goes down. Well, this starts at a minimum value and keeps raising like that. So that's really kind of nice. The vertical shift then, let's do an example of that. So let's just say I have, we'll say, oh, and by the way, I didn't do one of these, but if, well, and maybe I'll do it right now. I'll do it right now. I'm going to change the amplitude, but I'm going to have half sine x, but then I'm going to move that whole thing up 1. Okay, so the vertical shift is adding or subtracting a number on the outside. Okay, the amplitude is multiplying by a number. Okay, and so that here's what's going to happen here. So let's just say this is like, I'll go like this, and then we'll say this is 1 here, and we'll say that this is -1. So this would be -1/2, and then -3/2, right? And this would be 1/2, and this would be 3/2. And so, like, the regular sine would start at 0. Well, let's put these in. 2 pi, and then these are the halfway marks. So regular sine would start at 0, go up to 1, right? Go down. And then the 1/2 in front of a sine would just mean it would be going up half as high. And so it would compress that wave down. Okay? But this 1 here is also going to move it up. So it's going to move the whole wave up 1. So this oscillates about the x-axis normally. Okay? So this is going to oscillate around the line y equals 1 because the whole graph got moved up 1 unit. And the amplitude is going to be 1/2. So it'll start here, then it'll go up to 3/2, back down to 0, down to 1/2, and then back up. And that's not 0. I called it 0, but that's really 1, right? So it'll look like this. Okay, and so it's now oscillating between 1/2 and 3/2. Okay, and so that's the vertical shift. You can move it up and down. So let's say I would like this thing to oscillate between 0 and 5, right? So in other words, I want this thing to oscillate between 0 and 5. So I'm kind of asking a slightly different question because I don't have the function yet. But let's say this is 1, 2, 3, 4, 5. Here's 5. Okay? And I want this thing to start at 0 and go up to 5 and go up and down. Okay? So this whole thing is going to have to be shifted up. Okay, but it's not going to be shifted up to 5. It's going to be shifted to 2.5. So 1, 2. So there's like this halfway mark, right? And that's like the line y equals 2.5 or 5/2 or whatever. And we'll say this is like 2 pi. We'll say this is pi, and then this is pi over 2, 3 pi over 2. And now the amplitude, we want it to go up to 5, down to 0. So the amplitude from here to each of these is going to be 2.5. Okay? And then I'm going to use cosine, and I'm going to have it be negative. Okay? Because I want it to start at 0. Cosine normally would, if it wasn't negative, it would start up here at 5 and go down to 0. Go down to 2.5, down to 0, but this will start here and go up. So this is exactly what I want then. 0, like that, and then it'd go up to 5, back down to 0, and then down to there. So now this oscillates between 0 and 5. Oh, but I have to move the whole thing up 2.5 around this. So it's oscillating around the line y equals 2.5. So what I've done is I've stretched it out 2.5 and I moved it up 2.5. So it can start at 0, goes up to 5, and it keeps doing that. Okay, so now I can model this so that it'll actually oscillate between any two numbers that I want it to oscillate between. You can do that. So it's kind of neat. Okay. So now there's also something called the period and the phase shift. So let's just look at a couple of these. Okay. So let's say I have y is equal to, we'll say, sine of 2x. So what that 2 does here is it changes the period. So something multiplied by the x will change the period. Okay? And here's the relationship. So if I have something like y equals sine of bx, like this, then the period of the graph is going to be 2 pi, which is the old period, divided by b. Okay? And this will be the new period. So my b here is 2. And so my period of this graph is going to be 2 pi divided by 2, which is just pi. So by multiplying the x by 2, it makes the period half as long. Okay, another way of thinking about it is if I put pi into here, I would already be at 2 pi, and it would have completed the cycle, right? So that speed, the 2 speeds it up, makes it twice as fast. Okay, and so then what happens here is this period is now pi. So you think of the quadrant angles here as half of pi is pi over 2, and then half of pi over 2 is pi over 4, and then half of, or in between here, is 3 pi over 4. So those are like the 4 quadrant angles, and then it'll oscillate between 1 and -1, starting at 0, and so it'll go up, down, like this. Okay? And that'll look just like a regular sine one, and you wouldn't even notice a difference unless you actually did a regular sine, because a regular sine would go up like this, and then it would go back down, and then it would go. So the regular sine would take twice as long. This got sped up. It made it faster. Okay? And so the number in here changes the period. That's what it does. So let me give you another example, and this is kind of interesting. What if I had this? So we'll do like cosine of pi over 2 times x. So now my b is actually a radian. So let's see what happens here. So my period is going to be 2 pi, and then I'm going to divide by this b, which is pi over 2. Okay, so this would be 2 pi over 1 times 2 over pi, right? I'm inverting and multiplying. The pi's cancel out, and you get 2 times 2, which is 4. So this makes my period 4. So it makes it real numbers, and in fact, there's 4, this would be 2, this would be 1, and that would be 3. Okay, and so this is actually going to, the 1, 2, 3, 4 is going to be the 4 quadrant angles, right? And this is -1 to 1, and so cosine would start at 1 and go down like this. And so that's kind of neat, because now I have a scale of whole numbers there and not radians. So putting that there can change the scale, making it whole numbers. Okay? So let's not worry too much about phase shifts here, but let me just do one quick one just to show you. So the phase shift is just a horizontal shift is all it is. Okay? So let's say I do sine of x minus pi over 2. Okay, so if I'm adding and subtracting inside the function, that becomes a horizontal shift. Kind of like taking a parabola and shifting it horizontally. And it's going to, if this is a minus, it's going to shift it to the positive side. If it's a plus, it'll shift it to the negative side. So it's the counterintuitive shift, right? The vertical goes with what the sine is. The horizontal shift is counterintuitive. The minus goes this way, the positive goes that way. Okay, so basically, and this is a very, very simple phase shift, right? Here's 2 pi, this would be pi, this would be pi over 2, 3 pi over 2, and maybe I'll do negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. Okay, so normally sine starts, oh, let's do 1, negative 1. Normally sine starts here, it goes up, down, like this, okay? And this would be like down here, up, like that. Okay, and so this is basically moving this whole thing 1 quadrant over. So, like this point here is moving to there. So, it starts here, and it's going to go up like this. And so that's what that would be. Okay, and now if you move it a quadrant, it's pretty easy to do because you're just moving it over. But if this were something like, you know, pi over 3 or something, it's conceptually no more difficult. I'm just moving it a different distance, but actually pinpointing and stuff can get really tedious. And there are some techniques there. I'm not going to get into that. But what I want to do here is I want to show you, just do one that's really difficult. And I know there's a lot here, okay? But this is one that has everything in one problem. So it has an amplitude change, a vertical shift, this is a period change, that's a phase shift. So how do you go about doing this? Well, the very first thing, do not forget to do this, is that you must factor. And what do I mean by that? I mean, what I'm going to graph here is 3 sine, and then I'm going to take this 4 out, like that, and then this would be x minus, and now I need to divide that by 4, so that would be x minus 8, and then this would be plus 1. So in other words, if I distributed it back through, I would get 4x minus pi over 8. So when you factor 4 out, that's kind of weird because there's not an obvious 4 factor. There's not an obvious factor of 4, but you can still do it, and to factor it out, you're just dividing that by 4 to get pi over 8. But you want it like this because this is going to be your period change, right? This is the period change. Okay? But then you're going to use this as your phase shift of the graph with the new period. Okay, so this says use this as this is your phase shift. So you're going to have this period, but then this is going to be the phase shift, pi over 8. But it's not pi over 8 for the regular graph. It'll be the new period. Okay, so let me show you what I mean here. So first of all, what is my period? Okay, so it'll be 2 pi over 4. So it looks like it's pi over 2. Right? So this is 1 period. So half of that is pi over 4. Okay, half of that is pi over 8. And then half of that is 3 pi over 8. And then this would be like negative pi over 2. Negative pi over 4. Negative pi over 8. Negative 3 pi over 8. And this is kind of too bad because that's a single quadrant. I mean, it's good that that's a quadrant. That makes it easy. Okay, that's so you're just shifting it a quadrant. But this is the same shift as the problem we just did, isn't it? I have a sine, and I'm shifting it to the positive side, 1 quadrant. So that negative pi over 8 shifts it over 1 quadrant, which is what we just did, but that's okay. I wasn't thinking there. I made up the other one, right? So I didn't know it was going to do that, but that's okay. So now we're going to shift it up 1, and we're going to have an amplitude change of 3. So if it oscillates around y equals 1 and the amplitude is 3, then this thing's going to go up to 4, isn't it? So I'll do 4 there. This is negative 4. And this thing's going to oscillate, right, around y equals 1. Okay? And this will be like the maximum. The minimum is going to be 1, 2, 3 down. So the minimum will be like down here somewhere. Right? And the regular sine would start here and kind of go up, down, down, like that. Right? But this is going to move that over. So it's going to start down here, and then it's going to go up here, and then up to this, down here, and then down to this. Okay? Then this, 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 and this. So it'll be like this. Ooh. It would look like that. And then this would be so there you go. It would look like that. And that's kind of all put together into one. That's about as challenging as they get. But I want to do one more problem here, kind of a real-world application type problem. So imagine you have a desert here, and the temperature of the desert oscillates between a low of 40 degrees at midnight and then a high of 96 degrees at noon. And you want to find an equation that models the temperature where T equals 0 is going to be midnight, T equals 12 is noon. So this thing is oscillating between 40 and 90, right? And so we only need this positive quadrant here. And if it goes from a minimum up to a maximum, then it's going to have to go back down to a minimum. So the period is actually 24. Okay? It's going to oscillate every 24 hours. So then half of that will be 12. And half of this will be 6. And then half of this will be 18. Okay, now this isn't going to be perfect, but I'm going to do 40 and 96 and just assume that those are where they are. And I'm just saying that if I would draw the scale up, it might not be exactly correct there. And that's okay, because I'm just going to use this to try to come up with my equation, right? So it's going to oscillate between these two, so I need the number halfway between those, right? And that's going to be where my axis is. So where is my calculator? Here it is. Huh, I've done everything so far without a calculator. So to find the number halfway between these two, I'm going to average the two. When you average two numbers, you get the number halfway between them. And it's 68. So this would be 68. So whatever equation I use, it's going to be a trig equation that's going to be raised up 68. So let's start putting this together. Okay, what's the amplitude going to be? Well, from 40 up to 68, that's 28, and that's 28. So the amplitude is going to be 28, but it's going to start at the minimum and go up. So it'll be a negative 28, and since I want it to start here and not in the center, that makes it cosine. Okay, and now I need to know what the period of this wave is, or what the B is going to be for the period. Well, what do I do here? Normally, to get my period, I take 2 pi and I divide it by b. That's the formula, right? Let me move that up there. Okay, so I don't know what the b is, but I know I want my period to be 24 hours. So I can solve this for b, and when I do, I get this. Right? So to get the b, it's just like kind of getting the period. You just take 2 pi divided by the period that you want, and then you get what your b needs to be. So I want my period to be 24 hours. Okay? And so this reduces down to pi over 12. So that's what the b here is, pi over 12. And then you have the t. You're not going to need any phase shift here because the cosine will start at the minimum. But I do need the vertical shift. I got to move it up to 68. So given this, it'll start at 40, and then that's kind of the first quadrant, and then it'll reach that maximum of 96 degrees at noon, and then it'll be down to 18 and then down to 24. And so this would model the behavior every 24 hours as it oscillates between 40 degrees to 96 degrees, and it would just keep going like that. That's a nice application problem. It shows you how these can these trigonometric functions can model some real-world behavior. Okay, so this is a lot of stuff here. This is one of the longer videos. There's just a lot to explain. But something that would be good for you to do is to play around with this on Desmos. Desmos is a free online computer software, and it's probably a good chance maybe you've seen it in another class, or someone has mentioned it to you. It's absolutely free, and what I've done is I put a link right below this video. When you click on it, it will take you right to Desmos, and it actually has a sine and a cosine function. Let me show you what it does. And I don't remember the letters that it uses, but it'll have like some letter and then sine, and then it'll have some other letter for your b, and then x minus c, and then some letter out here, we can say d or whatever. Okay, and what it has are little slider bars. So you'll have one for each of these variables, like a little bar here, and it'll go from like -10 to 10 or something. And what you can do is slide this like this, and it'll change this number, and it'll visually change the graph. And it's just amazing because you can visually see. It's almost like an animation. So like you switch the B slider here, and if you moved it back and forth, it looks like a spring because it's changing the period of the wave. Or if you change that C slider, it'll keep going down like this, and it kind of looks like a river flowing or whatever. This D will move it up and down, and you can just play around and see how these things all affect the trig function. Okay, and possibly even you could use it to fiddle around until you can get it to model, some sort of behavior that you want. But Desmos is a great resource. It's free, so check it out and just make yourself aware of that. It's very easy to use, so you could even add to that and put in the tangent, let's say. And once you've played with it a little bit, it's very easy to do a slider. You pretty much just put the letter in, and then it'll ask you if you want to make a slider for that. And it's all almost self-working. Okay, play around with that, and I'm sure you will learn a lot. So there you go. That's graphing these trig functions. I didn't really talk about changing the graphs of the other functions. They're not quite as interesting because you don't have the amplitude and stuff like that. And you can change the period or whatever and speed it up, slow it down. But it's really these sine cosine graphs that I'm most interested in. So, okay, well, good luck with that.